Hello again, students. It's Mr. Keister here. We are still in Unit 11.2, and in fact, hopefully I should be finishing up Unit 11.2 today with this lesson. This is the second lesson on additional Voltaic cell calculations. We did the first lesson, the one previous to this, and so in our notes now, in fact, we ended up last lesson with determining using E values from the half reactions chart, how we can rank things as according to how good of reducing agents or oxidizing agents they are based on those values of E. So today we're going to pick up where we left off and talk about the relationship between EMF or E cell and Gibbs free energy. And then we're going to go on from there and hopefully again finish up Unit 11.2 today. So based off our original do nows here, this is Chem 2. We would have been doing this lesson on the 13th of April. I think if you're in Honors Chem, we're about 3 or 4 days behind that. But again, don't worry about these dates, because again, we have an updated document in Canvas that incorporates both the do nows and the due dates, which originally were on the calendar. Those are all now together in one document. So just make sure you're referring to that daily so that you can see what you need to be doing on a daily basis as far as lessons, videos, assignments, etc. So we will close this out here and pull up today's notes. And clear the screen or unfreeze it, and there we go. All right, so we're going to pick up today with EMF or E cell and Gibbs free energy changes. So in the study of thermal, which we did, I believe, back in Unit 9, remember delta H, enthalpy? Recall there was a method of predicting the spontaneity of a reaction using a quantity called Gibbs free energy. Whereby delta G was equal to delta H, the enthalpy, minus T times delta S. Delta S was entropy. So, and remember, entropy measured the randomness of a disorder of a system. So recall for delta G, remember delta G was measured in joules per mole or kilojoules per mole, either one. Recall that for these values of delta G, remember a negative value for delta G indicated that the reaction was spontaneous in the forward direction. A positive value of delta G indicated that the reaction in the forward direction was not spontaneous, but if you put the reaction in the reverse direction, then it would be spontaneous, as the signs would then flip. If delta G was equal to 0, all right, delta 0, remember that was the crossover point between spontaneous and non-spontaneous, then the reaction is what we say at equilibrium, whereby both the forward and reverse reactions are occurring at the same rate of speed. So let's go on here to the next page. Because the EMF of a redox reaction now, or E cell of a redox reaction, also indicates whether the reaction is spontaneous or not, then there's got to be a relationship that exists between EMF or E cell and Gibbs free energy. And this is it right here, whereby delta G, Gibbs free energy, is equal to the negative of N times F times E. Now, before we get going on that, if we put our little superscript zeros there, then remember that means at standard conditions, which is room temperature. Remember, room temperature for temp, 25 Celsius, standard pressure, 1 atm. And remember for E, that also means that the concentrations of the solutions, if any of our reactants or products are AQ, then those concentrations are 1 molar, okay? So N, let's talk about N. This is not moles, all right? This is not moles. Notice this is a little superscript N, all right? Or leaned, I shouldn't say superscript, but italicized N, whereby it's kind of leaning over. So this is the number of electrons transferred in the redox reaction, all right? So this is the number of electrons transferred. Remember, in a balanced redox reaction, your two half reactions values for electrons must be equal. That is the number we're looking for there. F is a constant known as Faraday's constant. This represents the quantity of charge, electrical charge, on 1 mole of electrons. That is equivalent to 96,500 coulombs per mole. That is also called 1 Faraday. All right, so this is the quantity of charge on 1 mole of electrons. E, of course, is the cell EMF, or E cell, of the Voltaic cell. So both N and F are positive numbers, all right? And so a positive value of E then is going to lead to a negative value of delta G, which makes sense because we said that for an operating Voltaic cell, E cell must have a positive value. And we've said that thermodynamically, for a reaction to be spontaneous, that its value for delta G has to be negative. And that would correspond here, okay? So when the reactants and products are all in their standard states, and again, we add the superscript 0 to delta G and E, just like we did up there, okay? All right. All right, so let's go to the next page and look at our first example here. So it's going to be very similar to what we've done previously, only now we're going to take it a step further and look at Gibbs free energy. So using the table of standard reduction potentials, calculate Gibbs free energy change, delta G, for the following reaction, all right? So here we have, again, a net ionic equation, an overall equation, redox, of course. And before we get going on the half reactions, so let's check and take a look and see what got oxidized and what got reduced. So here, silver and oxygen, O2, are both neutral elements, so the oxidation number is 0. Hydrogen and silver ions are already done there for us, although we know they're +1, respectively, for both of those. And in water, of course, hydrogen is +1 and O is -2. So in looking at that, what got reduced, of course, is oxygen, going from 0 to -2. And what got oxidized is silver, going from 0 to +1. Hydrogen remained +1 throughout. So silver got oxidized. So when we set up our half reactions, remember our cathode half reaction is reduction. Our oxidation half reaction occurs at the anode. So in looking at that, we can see that oxygen got reduced. So we are going to make sure we utilize a half reaction that involves oxygen. And of course, oxygen is located in water as well. So that's going to be found there. And of course, in water is also hydrogen. So I'm going to assume that probably the hydrogen is involved in this half reaction as well. So let's take a look here. So we're looking for the reduction of O2 in the formation of water. And as I look at the chart here, there are several. If we look on the right side here, about a little more than halfway down, you'll see that there are 3. I want you to please look at this while I am, so you can see how we can clear up the confusion here. There are 3 separate half reactions that begin with O2 gas. However, there is only one of those 3 whereby it forms water, and that is the first one of the 3 right there. So I'm going to write that one down, which is O2 gas plus 4 hydrogen ions, AQ of course, plus 4 electrons, yielding 2 H2O liquids. And as you can see, as I kind of surmised, this half reaction also involved hydrogen ions, which indeed it did. And so the value for the E of that half reaction from the chart is 1.23 volts. Our anode half reaction is our oxidation half reaction. That, of course, is going to involve silver. So now remember, again, that our chart is a chart of reduction half reactions. So we're looking for oxidation of silver. So on the chart, it's going to be in reduction format, so it's going to be backwards from what we're looking at. So we're going to be looking up the silver ion to silver, which is actually the very first one on the chart. Although we're going to put that reaction in reverse because this is our oxidation half reaction, not reduction. So writing it that way, we have Ag solid going to Ag plus 1 AQ plus 1 electron. Okay, and the value for E for that, again, we do not have to change the sign on that because, excuse me, we do not have to change the sign on that because of the math, the equation we utilize to calculate E cell. So that value is 0.799 volts. Now, remember our transfer of electrons has to be equal. The number of electrons released at the oxidation half reaction and the number of electrons gained by the reduction half reaction must be equal. In this case, they are not yet. And so here we have 4 electrons, here we only have 1. So we're going to have to multiply this bottom half reaction by 4. So that becomes 4, that becomes 4, and that becomes 4 as well. And so now we have these 4 electrons here are now equal. They will cancel. And if you then look, all the other coefficients come out to be exactly the way they are up here. Here's our 4 AGs. Here's our 4 AG plus 1s. Of course, the oxygen, the hydrogen, and the water were already correct. And we've just backed that up because we did not have to multiply that first half reaction by a coefficient. So our overall equation is now balanced by our half reactions being balanced as well. So let's calculate E cell. And remember, even though we multiplied this by 4, since E is an intensive property, we do not have to multiply that by 4. You don't ever have to do that. That value remains constant. So E reduction cathode minus E reduction anode. So we have 1.23 minus 0.799. And so our E cell value then is 0.431 volts. And as you can see, since that value is positive, that this is an operating cell, right? It will occur spontaneously and produce an electric current. All right, so now we want to calculate Gibbs free energy, all right? So the relationship between Gibbs free energy and E cell is this. A delta G is equal to negative NFE, whereby E is E cell, okay? So, negative. Okay, remember, again, N is not moles now. N is the number of electrons transferred in this reaction, which, as you can see now, is 4. All right, so that's negative 4. F is a constant, Faraday's constant, 96,500. And E, of course, is the E cell we just calculated, 0.431 volts. Okay, so we're just going to multiply those 3 numbers. This will give us an answer in our standard unit, which is joules per mole, minus 166, 366 joules per mole. Again, because all of these numbers are precise, we're not going to affect the precision level by our calculation, so we will not be doing any further rounding. And so this is the correct answer for delta G. Notice a positive value of E, which indicates a spontaneous redox reaction, also gives us a negative value for delta G, which indicates a spontaneous reaction overall. So those do coincide. If you were asked to put delta G in its standard format, normally, remember off our thermo chart, delta G was measured in kilojoules per mole. I mean, it doesn't ask for that here. If it did, of course, we just divide this by 1,000, and it'd be negative 166.366 kilojoules per mole. Again, it doesn't ask for that. Just watch for that on your homework or any other assessment, just in case you would have to do that. But this calculation here will give it to us in the SI or standard unit, which is joules per mole. This is the unit that is most commonly used, again, out of convenience, which is kilojoules per mole. So that's the relationship then between E cell and Gibbs free energy, delta G. All right, let me erase this real quick. And we'll move on to our next. Okay, so effective concentration. Remember in a, excuse me, in standard conditions that, we use little superscript O for E cell, that those conditions are room temperature, 25 Celsius. If any of our reactants or products are gases, then the pressure is standard, 1 atmosphere. And if any of our reactants or products are solutions, that their concentrations are 1.0 mole. Right? Those are standard. We've also seen that for Voltaic cells to operate, their redox reaction must be spontaneous. In other words, a positive value of E cell. And we know how to calculate EMF under standard conditions using our chart of reduction values. However, as a Voltaic cell's electrical energy is used, okay, so think about it. When you hook up a battery to a device, that device doesn't operate forever. Right? It doesn't operate forever. The electrical energy is used by that device. We're saying that is being discharged, right? Discharged for electrical work. The reactants of the reaction are consumed and the products are then generated. So the concentrations of those are changing. So if I come over here and look at our battery, or look at which is an example of a Voltaic cell. So remember the source of the electrons in a Voltaic cell comes from your oxidation half reaction, which is in the anode compartment of your Voltaic cell. So as we hook this device up to this battery and flip the switch on, that starts this half reaction going, all right? So the electrons are being released out here, running through the device, which utilizes the energy, and then the electrons are then being utilized over here in the reduction compartment, in the cathode compartment, whereby this half reaction is occurring, where reduction is occurring. Like I said, this isn't going to go on forever, because as this reaction is going on, the number of the electrons are being released, these reactants are being used up, all right? That battery is being discharged, all right? Ultimately, what do you think happens when all these reactants are used up? Well, you're right, the battery goes dead, all right? Its E value gets lower and lower and lower until it ultimately hits 0. Once it does that, battery dead. Throw it out, replace it. Unless you have a rechargeable battery, we'll talk about that a little later, all right? So, the EMF progressively drops until E cell equals 0, at which point we say the battery or the cell, a Voltaic cell, is dead. At this point, the concentrations of the reactants and products cease to change. They no longer change. They remain right where they're at. And we say that they are in equilibrium, or they are at equilibrium. Let's go to the next page. The EMF generated under non-standard conditions, non-standard, all right, can be calculated by using, it's a correctional value type equation. In this particular case, it's called the Nernst equation, all right? An equation first derived by German chemist Walter Nernst, who established many of the theoretical foundations of electrochemistry and the operating of Voltaic cells. So this is the Nernst equation. This is E at non-standard conditions, all right? E at non-standard conditions. Non-standard. This, of course, is E with the superscript O. This is E cell at standard conditions. And now here is our correction factor right here. So it's E cell minus 2.303 times R. R is the ideal gas constant. T is the temperature, all right, in Kelvin, over N. Again, this is not N number of moles. This is redox. This is N number of electrons transferred between the two half reactions. F, of course, is Faraday's constant. And then the other part to the correctional factor is the log of Q. All right. So let's talk about Q. All right. We'll do that over here. All right. So Q is the ratio of products to reactants. All right. Products to reactants concentrations. So basically what we're talking about here are reactants and products that are in solution, right? In solution. Okay. So, and those, and remember, for solutions, we measure concentration in molarity, all right? So, basically then, Q then is equal to product concentrations over reactants concentrations, all right? Okay. Now, if we have a product or reactant that's a gas, all right? So here I said for AQ, concentration is equal to molarity, all right? Concentration is equal to molarity. If we have a gas, this goes back to what we talked about back in Unit 8, all right? If we have a gas, we can convert a pressure to a molar concentration by using the ideal gas law, PV equal nRT, all right? Remember, N over V is equal to molarity, all right? So if we rearrange that equation, that gives us P over RT. So if we ever need to, we can take the pressure of a gas, divide it by the ideal gas constant and the Kelvin temperature, and that will give us its concentration in molarity, which we can then use up here to determine Q. And the other thing is solids and liquids. Remember, so we got gases, we got solutions. Solids and liquids are not included in Q, as their concentrations, which is determined by their density, remain constant throughout. So Q, which is the ratio of products to reactants, we only use reactants or products that are either in solution, and we use their molarities, or if they're a gas, we can convert their pressure to a molarity using the ideal gas law. Those are the only two types of products or reactants that go into this ratio that we call Q. It's actually called the reaction quotient. But anyway, solids and liquids are not used. Now, there will be, or there could be, an exponent up there. And that exponent is determined by the mole coefficient in the balanced equation. So if that comes up, we'll talk about that here in our example here. All right? So now, the nice thing about all of this is that the Nernst equation at room temp can be greatly reduced, all right? Because room temp, remember, is 25 Celsius. That's standard conditions for running a reaction. If this T is room temperature, 25 Celsius or 298 K, that would be a constant. T would not be varying. R is already a constant, the ideal gas constant. 2.303 is already a constant. Faraday's constant, F, is also a constant. So the only variable in this entire thing here that could possibly change based on the particular half reactions utilized is N, the number of electrons transferred. So we can reduce all of these constants, 2.303, R, T, and F, into one number, one constant. And there it is right there, 0.0592. So at T equals 25 degrees, which is the reaction, the temperature at which we run a reaction 99 times out of 100, the Nernst equation simplifies quite a bit to a much more manageable, or I should say less confusing or less intimidating equation. All right. So let's do an example here whereby our concentrations are not standard, and we'll see how the E value comes out there. So let me scoot this up here. Okay. The Voltaic cell from back in example 3 utilized the following reaction and operated spontaneously at 298 K. So we're at 25 Celsius, which is standard. All right, standard conditions. Its EMF at standard conditions was calculated to be E cell is 1.805 volts. All right, so we don't have to do all that work. We've already done it. Okay. What would the EMF of this cell now be when the concentrations are now 0.750 for fluoride and 2.25 molar for bromide? Remember, at standard conditions, those two concentrations would both be 1.0 molar. All right. Now they are not. So that's going to affect our value of E. The other thing I would recall from example 3 was that the number of electrons transferred in this reaction was N equals 2. All right. There was 2 electrons transferred in between those two half reactions. So let's look at this. So apparently the concentration or pressure of fluorine gas is still 1 atmosphere. We did not change the pressure, so that is unchanged. Bromine, of course, is a liquid, and so that concentration remains constant regardless. So these two are not going to be involved in our correctional factor Q, all right, the ratio between products and reactants. So let's do that first. So Q then is the concentration of the products raised to some exponent based on the mole coefficient over the concentration of the reactants raised to some mole coefficient there. All right, so the only product we have that is in solution that's involved in this ratio Q is F minus. And we are given that concentration right there. So that would be 0.750 molar, and the mole coefficient is 2, so that would be squared. Okay? Reactant. Well, again, fluorine is a gas. The pressure is standard pressure, so that is not changing, so that's not involved. But here we do have a solution in which its concentration has been changed. It's not 1 molar. So this then would be, you know what, I should probably, let me step back just a hair. let's go ahead and put this in here. So we have F minus 1 concentration squared, which was then 0.750 squared. Sorry about that. Probably need to have that step in there so you realize where that came from. So our reactant then that involves a solution whereby the concentration is not standard is bromide ion. And again, with that mole coefficient of 2, that would also be squared. So that's given up here 2.25 squared. So we take 0.750 squared over 2.25 squared. Again, I'm not going to round this yet. This is an intermediate calculation. It comes out to be 0.11 repeating. All right. There is no unit there because this is molarity, as is this, and those cancel. So it's 0.11. Okay, now we're going to use the Nernst equation to calculate E. So E is equal, whoops, that's not that E. That's that E there. So this is the E we're trying to find. This is E at standard conditions, or E cell, which we have up here. All right, minus our correctional factor. And since we're at standard temperature again, I should say standard conditions, 25 Celsius, 298 K, we can use the shortened version of the Nernst equation, which is 0.0592 over N times Q. All right? So we have then E equals, E cell is 1.805 minus 0.0592. The number of electrons transferred between these two half reactions that made this equation here was 2 times Q, which is 0.11 repeating. And again, sorry, I made a mistake here. That is the log of Q. So let me fix that. As you can tell, students, what day might I be giving this lecture for real? If you guess Monday, you are absolutely correct. This is a typical Monday mistake for me, and I have done it yet again. So I apologize. First period got that a lot from me. You guys remember that. That's where I tend to make the most mistakes at the beginning of the day. And actually right now, technically, we are in first period. So anyway, so this is the log of 0.11 repeating. So again, I apologize for that. Okay, so so this then is 1.805 minus 0.0592 over 2, which is 0.0296. And then this is a log base 10 of 0.11 repeating. And I'll put that in there, which is negative, and I'm not rounding that either, of 0.954 242509. So 1.805 minus these two multiplied together. And see, this is a negative value here. And so technically we are adding that. So that comes out to be adding 0.028 245578. And so when we add that to that, we get 1.833 volts. Now I'm rounding this to the same number of decimal places that E cell is, 1.833 volts. So the question is, why did E go up? This is E at standard conditions. This is E at the conditions we've been given here. Well, let's take a look at that. Br minus is a reactant, all right? At standard conditions, that would have been 1 molar. Here, it is 2.25 molar. So the concentration of our reactants went up. All right, it went up. Where are the reactants in a redox reaction? What starts a redox reaction? Right there, the anode, the oxidation half reaction. Bromine, bromide to bromine is our oxidation half reaction. If we increase the quantity of reactants in this compartment, then we have more electrons available to be released, all right, and work their way through the device, through the voltaic cell, which means the voltage goes up, all right? So we could also see here that our products concentrations went down, all right? They went from 1 molar down to 0.750. That's not really the determining factor here. I mean, it is part of it, but the important thing to realize here is that if you increase the amount of your reactants, which are occurring in your oxidation half reaction, then you're increasing the number of electrons that you can push through this cell and through this device, and so the voltage is going to go up. Okay. So there you have it. So this is the Nernst equation, which tells us what value of E we can have, excuse me, if we change our conditions that our voltaic cell operates from standard to non-standard, all right? And again, if the temperature remains at room temp, standard conditions for temperature, then the Nernst equation reduces quite nicely to a much shorter and more manageable equation, which is what you're going to have 99 times out of 100, because normally we run reactions, whether they be in a lab or a production facility, at room temperature. Okay. So there you have it. All right. So the last thing I want to talk about in this lesson today is batteries. All right. So let's erase that. So again, we'll be referring to that here in just a second. So a battery is a portable, self-contained electrochemical power source that consists of one or more voltaic cells. All right. The common 1.5 volt battery is a single voltaic cell, just like this one. All right. While greater voltages can be achieved using multiple voltaic cells connected in series together to form a single battery. So a battery can be either a single voltaic cell, such as this one. Like I said, the common AA or AAA or C series or D series batteries are all single voltaic. A 9 volt is as well a single voltaic cell. Like this one, our car battery, which is actually a 12 volt. Some of you probably know that. Are actually 6 2-volt voltaic cells connected together. When you connect them together in series, those of you that have had physics realize that if you connect those in series, that their voltages are additive. So if you have 6 2-volt batteries connected together in series, you end up with a battery that is 12 volts. And if any of you have ever opened a 12-volt battery, a car battery, you know on the top it's got the little cap there. If you lift those caps off, you will actually see 6 separate compartments in that battery, not one, but 6 separate ones. Each of those compartments is a 2-volt voltaic cell. In a primary or non-rechargeable battery, in the most common of primary 1.5 volt batteries, the alkaline battery. This is the battery most of us buy. These are a little bit more expensive than standard batteries. Why are they more expensive? Because they last longer, all right? Well, here's why. The following redox half reactions occur in your common alkaline battery. I'm going to make a note of this because actually this is a question on your test. And so the cathode reaction involves manganese, the reduction of manganese through manganese 4 oxide, I should say. So this is the reactant that is found in your cathode reaction. The anode involves the oxidation of zinc, all right? And so this is the reactant used in the anode compartment over here. And remember, it's the anode, well, actually it has zinc there. It's the anode compartment, remember, that drives the reaction. The EMF of an alkaline battery such as this is 1.55 volts at room temperature. Notice that we actually call these a 1.5 volt battery or 1.5 volts. When in reality, if you look up the values of E for these two half reactions and run it through our equation to calculate E cell, you actually get 1.55 volts. All right. The older regular batteries also have electrodes made of manganese 4 oxide and zinc, but it's the concentrated basic solution. All right, so in an alkaline battery, this electrolyte solution, all right, is KOH, which this is, K is a spectator on. All right, but our electrolyte solution, remember, that helps balance the neutrality of each side of the cell, it's the salt bridge, remember we talked about those, is strongly alkaline, all right? It's basic. What that does is, and that's why we call them alkaline batteries, because that electrolyte, that salt bridge, is a very basic ionic compound. In an alkaline battery, utilizing that basic solution is used as the electrolyte that makes alkaline batteries far superior. The consumption of reactants is slowed down considerably. So although the number of electrons running through the cell is constant, it doesn't affect its voltage at all. What it affects is the speed at which this goes through here. The slower it goes, the longer it's going to last. And if any of you have ever used regular batteries and then switched to alkaline batteries, you know this, that the alkaline batteries last far longer. It's not that their reactants are far superior. They're not. They're exactly the same. It's just that the electrolyte used here as the salt bridge, rather than being a neutral or acidic solution here, electrolyte, instead it's very basic. And that slows down the process. Doesn't affect the voltage at all or the performance of the battery. It just makes it last longer. So that's a good thing. I stopped buying regular batteries long ago. In a lot of devices we have nowadays, for our phones, for our computers, our laptops, Chromebooks, et cetera, we use rechargeable batteries. All right, rechargeable. In a rechargeable battery, such as a nickel-cadmium battery, nickel metal hydride, a lithium-ion battery, which are very big nowadays. Lithium-ion batteries are quite common. Lithium-ion batteries we've had some issues with. I don't remember if you guys recall the problems we've had with those hoverboards that use lithium-ion batteries. Those produce a lot of heat, and in fact, some of them produced enough heat to cause the reactants to ignite and cause a fire. So that, I think, has been now. I don't hear of that happening anymore now much. So I think they've taken care of that in the research lab and figured out how to fix that. But anyway, a lead acid battery, the one in auto batteries, of course, is also rechargeable. The solid reaction products of the half reaction at each electrode sticks to the electrode during the discharging process. All right. So as this reaction occurs and fuels the voltaic cell, the electrons are sent through, and then they form over here. They get the reduction half reaction over here. So those solid products stick to the electrodes. All right, they stick to the electrodes. So this is what is this? This is a nickel-cadmium battery. All right, so this is one form of rechargeable battery. The EMF for this particular nickel cadmium battery is 1.30 volts. While again, a car battery is a series of 6 2-volt lead sulfuric acid voltaic cells connected together. As the battery becomes weak, in other words, as these reactants are used up, all right, and goes through here, you get a buildup of products over here and a reduction of reactants here. The value of E gets less and less and less, of course. If it gets low, of course, your light comes on. If you got an alternator problem in your vehicle, that light will come on and you'll see your lights going dim and things not working electrically correct and all that good stuff. So as the EMF approaches zero, the electrode reactions can be reversed during the charging process. So if your alternator in your car is working correctly, that is happening continuously as your car is running. And so thus it stays fully charged at all times. Unless, of course, you have an alternator that goes out on you, which I have had happen several times over the course of my car driving career. But we can, now if it's a battery at home, such as in your phone or in your computer, this is why, of course, we have a charger, all right? So when we charge the battery, charging is just the opposite of discharging, all right? So if the discharge of a battery means we're sending electrons from oxidation to reduction by this method, then when we hook the battery up to a charger, what it does is reverse the flow. It reverses this process. So then we utilize this reaction as oxidation, this one as reduction. We flip the process around and we send the electrons back, all right? Now, the charging process is not 100% efficient, all right? Every time you charge a battery, there is a small portion of this that through the course of the reaction, it's not 100% efficient. And so a very small portion of this remains unreacted. In other words, you can't send them all back. And so you can't recharge a battery forever. Those of you that have phones know that. All right, I've had batteries go bad on me, and I'm sure many of you have as well. Same thing with a car battery. They don't last forever, okay? Because that recharging process is not 100% efficient. It does make them last a whole lot longer, and if you look at a rechargeable battery versus a regular battery, even an alkaline battery, rechargeable batteries cost a lot more, but think about it. How often do you have to replace them? Okay, so, there's a give and take there in regards to cost. We like rechargeable batteries because of their convenience. I certainly remember when calculators I have a calculator at home that still takes regular batteries, all right? In fact, it's my first calculator I got when I went to college. It's a great calculator. It does everything it needs to do, but it doesn't have a solar-powered rechargeable cell in it, and so I got to replace the batteries. So, but anyway, so as the battery becomes weak and the EMF approaches zero, the electrode reactions can be reversed when you hook it up to the charger. All right, it reverses the flow. We recharge back up, and you're ready to go again. Again, it doesn't recharge 100%. So when that says 100% on your phone, maybe lying just a little bit. All right, you'll notice as your battery gets older, it seems to weaken quicker, and again, that's kind of reflected in this right here. So those are rechargeable. Fuel cells. Many substances are used as fuels. Most often thermal energy is produced by the combustion of those fuels, and this thermal energy is then converted to electrical energy, usually by a steam turbine generator system like we use in a power plant. All right. Usually only a maximum of 40% of the energy produced by the combustion is converted to electricity. So it is not a super efficient process. This is why we're looking at other types of electricity generation procedures, such as wind turbines and hydroelectric power with dams, solar power with using photovoltaic cells, and things like that, because they're much more efficient than producing electricity through the combustion of some type of fuel. The direct production of electricity from fuels by voltaic cells could in principle then yield a much higher rate of conversion of the chemical energy of the reaction. And the fuels are not combusted, so there's no pollution of any kind released in the environment. So this is this is why we're looking more and more towards these alternative ways of producing electricity. Voltaic cells that perform this conversion using a conventional fuel, though, such as hydrogen or methane, are called fuel cells. Now, we are starting to use natural gas or methane as a fuel in public transportation vehicles. In fact, right here in Lafayette, I don't know if you've noticed the buses that are used for those. A lot of them say compressed natural gas, right? So they're using a methane fuel cell to power their vehicles, to power those buses. It is much more efficient than a standard combustion engine, all right? Much more efficient. So here is one. Here's an example of a hydrogen fuel cell. Not a methane one, but a hydrogen. Whereby the cathode, the reduction half reaction, involves the reduction of oxygen, and the anode involves the oxidation of hydrogen. And if you look at these two half reactions and you calculate E cell, you get about 1.23 volts. But I want you to see what the products of the reaction are. The net ionic equation is the production of water. Now, in a methane fuel cell, you are still going to get the release of some carbon-based emissions, which of course add a little bit of pollution to the air. Not nearly as much as combustion, as pure combustion, but certainly still some. In the use of a hydrogen fuel cell, the only chemical product is water, right? And so, which is non-polluting. So the use of fuel cells as electrical energy sources has increased dramatically, all right, in the last 20 years as technology has improved. And I certainly expect to see that they are used even more and more. Now you're starting to see solar-powered homes and businesses. In fact, there's a new array of solar voltaic cells set up right off of New 231 as you're driving south. There's one out there. It's only been up there, I think, maybe a year or so. But anyway, that's another example of this. So as technology improves, we will use those more and more and more as electrical power sources involving stationary power plants, temporary or supplemental power sources for towns, businesses, and homes, and also, as we just said a little bit ago, for public transportation vehicles. So all this kind of research is ongoing. Like I said, if you want to relate a chemistry topic to some real-world applications, electrochemistry and redox reactions, voltaic cells, look no further than that. We're talking about a multi-billion-dollar industry. You know, the need for energy in our society continues to escalate on a daily basis. You know, more and more of the things we utilize to live the way we do nowadays all depend on the availability of energy to power those devices. And so as we continue increasing our need for that energy, the increased research in voltaic cells, electrochemistry, fuel cells, any type of those type of things that produce more energy in a more efficient way and a less polluting way just become more and more valuable. There's a lot of jobs out there in industry related to electrochemistry and energy. Keep that in mind as you move through your career choices. All right. So anyway, I believe we have reached the end of Unit 11.2. So this is the last lesson in that unit. We have a lab coming up here soon that I'll be putting out in the next several days. Be on the lookout for that. the Unit 11.2 review assignment. As that is posted and made available to you, you can certainly be doing that. You should have the paper copy or have access to a paper copy already. So be thinking about that as you reach this stage of your lesson. So again, that reaches us to the end of Unit 11.2. A lot of info in this unit, but a lot of really, really good info in relation to how we use electrochemistry in our world today. So this is Mr. Keister signing off. I'll catch you next time. Thanks for your attention, and stay safe, everyone. I miss seeing you, and but I think about you all the time. So take care of yourselves, and I'll catch you on the next lesson. This is Mr. Keister signing off.